Last time we started section 3.2, addition and subtraction of whole numbers. And I believe we're on the basic addition and subtraction strategies. Does that look right to you guys? Okay, so there are some basic addition subtraction strategies. Some of these you probably know and love. You use them all the time. Others of them you might be like, oh, I never thought to do it that way before. Isn't that interesting? So we'll see how that goes. All right, so the first basic addition strategy is the counting on strategy with addition. So when you're adding numbers together, so let's say you'd like 3 plus 4, typically a student would start with the larger value, like the 4, and then they would go, watch my hands, 5, 6, 7, 8, or whatever. I said 4 plus 3, didn't I? So 5, 6, 7. So they would count on from one number up that many to whatever number you're going to after that. So that's the counting number, starting with one value and counting up the additional amount to the other value. Doubles. This is one that has become more popular. You will see this in more of your textbooks and resources and things than you used to once upon a time. So children, if they know their doubles, they know what 1 plus 1 and 2 plus 2 and 3 plus 3 and 4 plus 4. If they know their doubles, what they do is they think of the numbers as doubles. So when we have like 3 plus 4, they think about it as 3 plus 3 and then plus 1. Okay? So it is a strategy. It helps some students. So whether we like it or whether we don't isn't really the point. Okay? The point is that it's an additional strategy. Okay? So if you knew what 3 plus 3 was and you wanted to do 3 plus 4, you just add 1 on to your sum that you know. Making 10. This is an interesting one. I do this with estimation. I do this when I grocery shop sometimes. So making 10 is a method for adding a value to 10. Including leftovers. For example, if you did 8 plus 6, basically instead of doing 8 plus 6, you would do 8 plus 2, and then add the additional 4 after that. Okay? You add to get to 10, and then once you get to 10, you just have that many, however many is left over more. Okay? So you have 10 plus 4 is 14. A couple more. Counting backwards. So this is like subtraction, right? So if you were subtracting, you would start with the higher value and then count back to the lower one. So if you did something like 10 minus 5, you do 10 and then you count backwards. It's like counting on. 10, 9, 8, 7, 6, 5. So we count 5 backwards. That's the counting back strategy. The counting on, which sounds like counting up, but it's not exactly the same thing because it's used for subtraction. You start with the lower value. So again, let's do my 10 minus 5 example. You start with the lower value 5, and you count up to 10. So you go 5, 6, 7, 8, 9, 10, and you stop at 10 because that's the number your goal is. Your goal is to get to 10, and however many you counted up, in this case the 5, that would be your answer. So you're counting from the lower value up to the higher value, instead of going from the higher value down to the lower value, which was the counting back strategy.
So what's the main difference between the counting on addition and subtraction?
Counting, this one over here, counting on with addition means that you're, first of all, you're just dealing with addition, and then you're counting however many numbers you've got. So like on this one, if you started out with, I need to change my colors just a sec. 3 plus 4, again, you probably would start with the larger value, but you start with the 4, and then you'd count how many more you needed, 3 more. So 4, 5, 6, 7, your answer is 7. If you're doing the subtraction one over here, you've got something like, and I won't use 10 and 5, how about I use 10 and 3? 10 minus 3. Then you start with the 3, and you count up until you get to the 10. You don't count 10 more up. You just count until you get to the 10, and then the number you counted to get there would be your answer, in this case 7. All right, I want to move into subtraction, and subtraction has some interesting features with it. So subtraction, for any whole numbers a and b, where a is bigger than or equal to b, then a minus b is the unique whole number, c, such that b plus c equals a. I've seen like faces like grimacing. Oh my goodness, you guys don't like this definition, do you?
Oh, mine's crazy too.
Oh, it's showing up funny in your text. Well, that's better. Okay. All right, jot those down correctly. I don't know how you can PDF something and that happens. It doesn't make any sense.
I was trying to
Sorry.
write it down.
Okay, so A and B. A is bigger than or equal to B. B minus A is the unique whole number C. such that B plus C equals A. Okay, so this is actually the way in which kids first learn to subtract, most of the time. So when you're talking about something like 7 minus 3, is you say 3 plus what equals 7. And the reason that this is helpful is because kids already know addition and subtraction. They know the addition facts before they get to subtraction. So they've already worked with the flashcard or the computer program or the whatever, and they know that 3 plus 4 is 7. They know that part. So if you can change it into an addition equation that they know, they can fill in the missing blank. Okay, and that's exactly what this says. This blank is the location where you see the C. The reason this answer is 4 is because 3 plus 4 is equal to 7. That's what subtraction is. It's filling in the missing piece. And in fact, that's one of our models of subtraction you're going to see here in just a moment. I think we have 3, 4. I'm just wrong. We have 4. 4 models for subtraction. So we have everybody in class today. That's kind of cool. I've had lots of people gone throughout my last couple of days here. So what I'd like for you to do before we actually even get into this is I'd like for you to get up and move to where your group work partner is. Does everybody get the group work partners like last time or 2 times ago or whatever? I'm going to go through the 4 basic strategies or models, what they call them models, for subtraction. There's 4 basic models for subtraction. These models of subtraction are very differently worded types of questions, but they're all resulting in subtraction. Okay, the operation which we do is subtraction, but they set up differently. So after I do the 4 examples, what you're going to do in your groups is you're going to create one of each of the types of 4 examples. That's what we're going to do. Okay? So pay clear attention to try and make sure you very well understand the difference between the strategies that are presented, okay, the models that are presented. All right, here's the first one. This is called the takeaway model. This is the one that probably is the most common in our mind. In fact, some people will describe subtraction as takeaway. Okay? So it says Abby had 24 rocks. Eli sneaked into her room and took 5 of her rocks. How many rocks does Abby have now? Okay, so she has them, she owns them, they're part of her personal property, and somebody takes something away. That's what take away means. Okay, you actually have it, and then there's pieces of it that are removed. Now, in terms of drawing pictures for it, there's also the strategies, not strategies, but the concrete models for the pictures. So I will draw the pictures for what we have. So I want you to draw 24 rocks. Okay, I have 24 rocks. Do you have 24 rocks? Okay, and then Eli comes in and he steals some, right? He takes some away. How many does it say he took away? 5. So we're somehow removing these 5. And the question is, if we were to count how many we're left with, what would we get? 19 rocks. So the picture is a concrete model of the answer. But this model is the takeaway model for subtraction. Because we have it already and somebody is taking it away.
So does takeaway mean you want to draw a picture? Like in our
No, not necessarily. It's not about the picture that's being drawn. It's about the wording of the question that's being asked. That's what makes this takeaway. It's the wording of the question being asked.
So like when we do it in our homework, we don't necessarily have to like do a picture.
No, you wouldn't have to. No. Okay, missing add-ins. This is different. Lilise needs to collect 10 leaves for a school project. She and Temesky go out and find 8 leaves. How many more leaves does she need? This is not takeaway. She never had 10, right? She's trying to get up to 10, but she doesn't actually have 10. This is not a takeaway model. This is missing add-ins. She's missing something she needs. So in terms of the picture for this, the way that you usually see these drawn is you usually see the number that they already have. So in this case, they have, what was it, 8? Yeah, I know these do not look like leaves at all, pretend. Were they beautiful? Okay, we're going to make them look kind of long. How's that? Okay, so here's 8 leaves I have. And then we're missing a couple, right? That's exactly what we're missing, in fact. What are we missing? Well, we're missing 2. See them dotted? We don't actually have them, but this is how many we would need in order to have 10 of them. And then the answer is the ones that are in dotted form. The answer is that there are 2 leaves that we still need. So again, this is the concrete picture for this model. The model is missing addends. You can also do this model where you actually write it out. So something like this, 8 plus blank equals 10. So this would be like an equation form of writing this out, right? First one, concrete model, means we've drawn a picture of the actual event, and then this would be the equation form of that. The nice thing about this missing addends model, kind of like the definition of subtraction in and of itself, is that it leads very nicely into algebra. Far too often people think, and maybe you sometimes think it yourselves, equals means and the answer is. Right? But the answer here is not on the other side of the equal sign, is it? The answer is the missing piece on the left-hand side. So that leads much more nicely into an algebra type of a thinking with that particular equation. All right, your next one, comparison model. Madeline and Monique play basketball. Madeline scored 12 points. Monique scored 8 points. How many more points did Madeline score than Monique? This is not takeaway. This is not missing addends. You're comparing 2 values, which still means it's subtraction, right? It's still a subtraction problem, but it's presented quite differently. So what does it look like, or what could it look like if you were doing a concrete model for this one? Well, it could look something like this. We've got them playing basketball. We have Madeline scoring 12 points. Maybe it looks like tally marks. And then you have Monique scoring 8. And so you're sort of just pairing them up, and you're noticing these guys are missing their counterparts. Kind of left out there to dry, right? This is my answer. The answer is 4 points. That's how many more she has. There's nothing special about tally marks, but they work okay. The last model, let me make a comment. All 3 of these models so far are used for sets, for whole numbers of objects. I can't talk about scoring a half of a point in a basketball or half of a shot, right? That doesn't make sense. I can't talk about collecting half of a leaf or having half of a rock, all right? So all 3 of these models so far would be the set models for subtraction. The last one is actually what's called a measurement model. So it is often done with a number line. We had a number line or measurement model for addition last time. So this one would be something like this. Akeem drives 15 miles to the mall. As he's on his way home, his mom calls to ask him where he is. He states that he's coming home and he's driven 8 miles so far. How far is Akeem from home? So what I want you to notice is that what we're counting in this case is not objects. We're counting a distance. That's why it's a measurement model. Okay? Anytime you're dealing with a measurement model, you're measuring some length of something. So last time I think we were measuring feet of aluminum and wood, right? This time we're measuring length or distance of a mile. Okay, so these are all objects where you could actually talk about half of it and it would make sense. Okay, half of a rock doesn't make sense, half of a mile does. That's what makes it a measurement model. So for this one, a measurement model, a concrete picture of it would look like a number line. So like the answer part of it. So we have our house. There it is. There's my house. And then we have the mall. Much bigger. I don't know how to draw a mall, but we're going to pretend. Okay, so there's mall. And what do we know? We know that they're 15 miles apart, correct? So this whole length is 15. And he says that he is 8 miles from the mall. He's driven 8 miles so far. So this is where he's at. He's 8 miles back here. And the question is, what distance then does he still need to go to get home? And the answer would be 7. He is 7 miles still from home. His mom's probably calling because it's dinner time and he's not there. Just guessing. Okay. Any question about this one? Notice this is missing add-ins. Can you see how this is a missing add-ins kind of model, but it's with measurement? The measurement models can take on the form of any of the other ones, right? It could take away a take on, it could take on a takeaway kind of model, right? I have, 5 feet of fencing. And the neighbor steals a feet of fencing, I don't know, whatever, and you remove part of it. So you can use any of the other 3 models with measurement. Measurement just means that it's a length of something, okay? All right, so here's where it's audience participation time. You have 2 group work partners with you today. Everybody does. And you're going to create one of each of these 4 types of models. So you're creating word problems. And use this time effectively to think through it. Make sure you understand it clearly, because I have been known to ask questions like these on the tests, where you create one of these on a test. I have been known to do that before. So go ahead and find for me 4 models within you and your group, something that you're going to feel comfortable enough for somebody in your group to say out loud. So let's keep things very appropriate, okay? All right, so some group, tell me, what did you write down for your takeaway model? Brianna.
We said Dr. Hands has 7 machines in her desk. After the test, her students snuck in and took 3. How many cookies does Dr. Hands have now?
Excellent. So we took away cookies from Dr. Hand's desk, which would be a really bad idea. All right, another group. What did you do for takeaway model?
We did cookies too, so we said Mom baked 14 cookies and Sally ate 5 of them. How many cookies are left for the 14?
All right, I hope you guys aren't hungry, because we've got 2 examples now with cookies. Do we have more examples with food later on?
Yeah.
This happens every time I do this exercise. So, all right, how about the second one? What's our next one? Missing add-ins. So some group that hasn't taught, tell me what you got for missing add-ins. What you wrote down.
Jackie needs 6 crayons for art class. She only has 3. How many more crayons does Jackie need?
Excellent. So we've got some missing crayons. Yeah.
Gretchen Wieners wants to buy a $6 lipstick. If she has $2, how much more does she need to buy the lipstick?
Okay, so we're having money and we're doing lipstick. Okay. Maybe not appropriate for the 4-year-old in the class, but would work if you have junior high kids, right? Absolutely. Okay. How about comparison model? Okay, which group has not talked? Selena, is that your group? Hannah? Abby, one of you guys, tell me what you have for the comparison model.
Kyle has 5 pennies in his piggy bank. Jimmy has 3. How many more pennies does Kyle have?
Excellent. That'll work. Okay, one more example of the comparison model. I know everybody's actually given an example now, so somebody that's going to talk again. Okay.
Joey ate 4 pizzas while Ross ate 1 pizza. How many more pizzas did
They ate a whole pizza?
Yeah, Joey.
It's Joey from Friends. You can eat 7
Okay,
pizzas.
we're eating lots of pizzas. Okay. Who knew? All right, and then our last one, measurement model. So somebody tell me what you got for your measurement model. What did you write down?
Amy is coming back from Starbucks. The drive from Starbucks to OBU is 18 miles, and she stopped to get gas after 7 miles. How far away from OBU is 18?
Okay, sounds good. And then Abby?
It takes Mark 5 minutes to walk to class, and he is walking 3 minutes. How much more time does he have until he gets to class?
Very good. So now we have a measurement model. That's a good one. I'm glad you brought that up. The measurement model that wasn't about distance, right, or length. It was actually about a length of time, which can also be subdivided into something that would be decimal amounts. Okay, excellent. All right, we are going to talk about some whole number properties for subtraction really quickly to finish this section out. The question is, we had 4 properties of addition last time, and the question is which one of the ones of the 4 actually hold for subtraction. So the closure property. The closure property means if I had 2 numbers that are whole numbers and I subtract them, do I always get a whole number? If I take 2 whole numbers and I subtract them, do I always get a whole number?
No, because you get negative.
You could get negatives. So this one does not hold. If we were doing integers, which we will be doing toward the end of this class, not today, but at the end of the semester, that'd be okay. But this one doesn't hold, and the reason is because if I took, say, for instance, 3 minus 5, that's equal to negative 2, and negative 2 is not an element of the whole numbers. It's not a very good W. Okay, not an element of the whole numbers. So it's not closed. Subtraction, the whole numbers is not closed with subtraction. How about commutative? Commutative means the order doesn't matter. Brianna, you're saying no. Why?
Because, like, if you switched 3 minus 5 to 5 minus 3, you get positive 2, which is a whole number.
Yeah. So if I take 5 minus 3 or I take 3 minus 5, I get different values, and the two values that I'm getting, of course, are not equal. They are negatives of each other. And that's actually the kicker, right? I mean, like, commutative means that the order shouldn't matter, and it does if I do subtraction. How about associative? This one you might actually have to write one down to see whether it works or not. So let's give it a try. Let me see what one I actually wrote down in my notes. How about 3 minus 2 minus 1 compared to 3 minus 2 minus 1? Okay, so I've got the subtraction in there twice, just like I'm supposed to. But I have to do order of operations, meaning the parentheses happens first. So on the first one, the left-hand side, 3 minus 2 is 1, and then 1 minus 1 is 0. On the right-hand side, I have to do the 2 minus 1 first. So the 2 minus the 1 is 1, and 3 minus 1 is 2. So those are not the same. So we don't get associative property for subtraction either. And then the identity. This one always throws people a little bit. The identity. Well, the identity property for addition said that if I take the number 0 and I add it to the number 5 or whatever, 0 plus 5 and 5 plus 0 both equal 5. Right? Okay, so some people might want to say that there's an identity for addition, for subtraction, same as addition, that it's 0. The problem is it only works in one direction. This piece works just fine. This piece, not so much. The identity has to work in both directions, and it only works in one direction. So this isn't really a thing, but you kind of look at this and feel like, well, it's kind of like half of an identity. There's no such thing as half of an identity, but that's how it feels. It feels like this is half of an identity. All right, any questions on that one? All right.